Yeah, so this is chapter 21 is all about breaking the rules. All the rules of ultrasound are going to be broken or altered. And when we violate those rules, we usually get an artifact on our screen. So starting on page 355, types of artifacts. Well, they're not real generally, or they might be real something, it's just misplaced. Not seen on the image. So yeah, you could have an artifact of not seeing something when you really should be seeing something. Incorrect shape or size. Yep, that's refraction of sound, speed differences of sound. Incorrect position. You know, something's placed not quite in the right spot on our screen. That happens as well. And incorrect brightness. So too echogenic, too hypoechoic for what the tissue should be showing. Those all happen. And causes of artifacts. Number one, violation of assumptions. We'll talk about assumptions in a second. Equipment malfunction, of course. Physics of ultrasound, of course. And operator error. No, that would never happen. We never have operator error. And let's see. 14 participants. I know two students did say that they were not going to be able to make it, but anyhow, image characteristics: hyperechoic, hypoechoic, anechoic, isoechoic, homogeneous, heterogeneous. Let's go over those again. I know we've talked about these already, but we had to talk about these, otherwise we wouldn't be able to speak really about ultrasound or about the screen. Artifacts in general. Hyperechoic or echogenic. Well, that doesn't look hyperechoic or echogenic. So these splotches of color they represent just tissue. Whatever tissue, does not matter. It's just a graphical representation of tissue. So if I were to say I wanted to see something hyperechoic in that tissue, well, that's very hyperechoic. Can't get any whiter than white, or brighter than bright white. So it is hyperechoic. It's also echogenic, is another term that they didn't use right here on page 356, but it's a common term, so we should use it. So that's hyperechoic. Actually, let's show some other hyperechoics. That I know it's a different color entirely, but that is bright. Let's see if I can do this with. Okay, that's actually better. That second dot that I've put in, I wouldn't call it echogenic. In my language, echogenic means very, very bright. Hyperechoic can be very, very bright, but it also could be simply brighter than the rest. I was thinking of a stupid joke on one of you guys, but forget it. So this second dot that I've placed here is brighter than the tissue, so it is still hyperechoic compared to that tissue. It might not be hyperechoic compared to some other tissue. Well, in fact, let's just say this is tissue out here. There's my little piece of tissue, and then there's a circle of darker tissue. It happens to be the same color. Oh, that's weird. It doesn't look like the same color. These two are the same echogenicity, but they're called completely different things because of the background that they're laying in. Over here, it's hyperechoic because it is brighter than the rest. But here, it is actually hypoechoic because it is darker than the tissue around it. So let's just get rid of a few of these things. So hypoechoic, let's see, I'm just going to do this, choose that color, and then just go a little bit darker. Okay, so now that dot is darker than the rest. It is hypoechoic. Let's see. Wrong color. Well, it's hard to tell. Let's hit it again. Okay, slightly different now. Okay, well, forget it. They're hypoechoic compared to the tissue. Anechoic is an absolute value, and meaning without an echo, well, echoes, without echoes. So an anechoic structure would be like that. Usually assist, not always, but usually assist. Sonolucent is another term for that. There are no echoes returning from that area. That's why that area is black on the screen. Isoechoic, let's just do, let's see, if I have a structure there and then another structure, we could say that those two structures, those two dots, are isoechoic to each other. I could also, so those are like maybe those two little lesions are isoechoic to each other. But I could also say that this tissue over here, we'll just separate it by a slight whatever. Those two tissues are isoechoic because they're the same echogenicity. The same average number of echoes is coming back to the transducer from each one of those tissues. All right, homogeneous. Homogeneous. Homo meaning the same. Let's see, I think I was going to use this for homogeneous. So this tissue that I'm creating here is more or less homogeneous. Yeah, sure, there's variations in it, but for the most part, you're getting the same texture. Yeah, I'm going to write that word down. I like that texture. More or less the same texture. Your thyroid should be homogeneous. Your liver, most of our tissues, most of our organs should be homogeneous. And so that's usually a normal situation. But then we might get into something that's no longer homogeneous. Let's actually, we can put little circular tumors in here. Whatever. You get the point. Heterogeneous or heterogeneous, depending on how you prefer to say it, is tissue that generally is unhealthy. We don't generally want to see heterogeneous tissue in the body. It usually means there's something wrong. Okay, well, that's all review. And these assumptions that I wrote down here are also review. Let's go through these carefully here. Assumption 1, sound is always the sound beam is always, let's say, straight down. A straight line, that is the assumption we make. And the echoes are a straight line back to the transducer. There's the other assumption. Those are the first two assumptions. The computer has to make these assumptions. The engineers, the people who develop these things, they have to make these assumptions. You can't just assume that everything's random. But as you can imagine, as sound travels, it hits different tissues with different speeds of sound, refraction. We already know that echoes, the true shape of an echo coming back, spreads out. So these assumptions are not 100% correct. Sound always travels at 1540 meters per second. We have some pretty cool artifacts when sound doesn't travel at 1540 meters per second, or 1.54 millimeters per microsecond. So that assumption is false. It's just an average. Reflections only come from the beam. We've already mentioned side lobe and grating lobe artifacts and how they can create an artifact because it is sound, it is an echo from somewhere other than the beam. Imaging plane or slice thickness, we've talked about that already, it's very thin. That's another assumption. And we also assume, or the machine assumes, that the echo strength perfectly demonstrates the reflector characteristics. And because of attenuation and the TGC curve not always being perfectly correct, that's hard to say that the echo strength is always demonstrates exactly what the characteristics are. They try pretty hard to get it right, but they're not always correct. Okay, so those are our assumptions. Let's break some of those assumptions. Reverberation. We've all seen reverberation, whether you know it or not. The first time you saw it, or the first time you really recognized it, is when we were scanning Tupperware. We had a little Tupperware container. In fact, see, I put this line in as skin, but we'll just here. Let me throw a Tupperware container here, filled with water, and what you saw, if you had too much depth on your screen, or if you got the transducer too close to the bottom, is what we ended up seeing is sound going in, reflecting back, which is good. By the way, very, very bright reflector, basically pretty much 100% reflection, almost negligible amount going through. So it was a very bright line represented the bottom of the Tupperware. And if you got a little closer, or if you changed your depth so that you saw more, or you waited longer for more echoes, we would also see another reflection, and then another reflection. And this is sound literally bouncing back and forth between the face of the transducer and the bottom of the Tupperware. So what did we see on our screen? We saw, well, I'm going to use a dark line to represent a bright line. But we saw, let's see, a bright line on our screen, which, let's use a different color. Salmon. I don't know why I'm using salmon, but I am. All right. The first line represented the true echo, the true reflector, the bottom of the Tupperware. Whoop, top. But then we would see, oh, we gotta make our measurements correct here. We would see another line. And if we had it deep enough, looks like we do. Yike. Yep. We would see yet another line. So let's call this real, fake number 1, fake number 2. Real, the first echo going back is real. Fake 1. Fake 2. So that should make some sense. We're assuming, the machine is assuming that this doesn't happen. But it can't make that as well. It has to make that assumption, but it can't know that the second grouping of echoes that came back was fake, was a reverberation bouncing back and forth. And that the next one and the next one and the next one, you can't know those things. Okay, so that was Tupperware. We've seen this also in our carotid arteries. I kind of have this at an angle here. Let's see, we have a very bright echogenic wall of the artery here. Maybe, let's see, do I want to use? Yes, now I'm going to use then a layer. There's fascia, there's different muscles in here. So let's just say that's muscle. And then fascia. Yeah, okay. So that fascia can be seen more than once due to reverberation. Let's see, how do I draw this and make sure that I'm not? Well, the beam, of course, let's just draw one here. The beam line coming all the way through. It's going to, a little reflection there, a little reflection there, there, and so on. So those are all the normal expected reflections, and we do get those because we have a picture. But some of the things that could also happen is, well, let's see, you could have some beam, some portion of the beam come down to the wall here, which is a pretty echogenic wall. Reflect back, reflect down, and reflect all the way back. Some portion of the beam, not the whole beam, but some small percentage of the beam is going to actually do this. So let's think about that. That's 1, 2, 1. Let's see. If I need using this guy. He's going back and forth, back and forth. So then I'm going to see there's different ways this reverberation can happen in several different ways. So I'm trying to think about what I just drew here. Got to be careful. If I'm seeing that wall twice, okay. So the way I drew this, I'm going to see the wall of the of the carotid artery again. And if it's bright enough, I'll see it again and again and again, just like with the Tupperware. Okay, so I might see kind of an echogenic line running right down the middle of my carotid. Well, that's a little scary. I mean, are we possibly looking at a dissection? Is that real tissue? So that's something. Every time you see it, you'll become very accustomed to seeing it, but always take a second look. Make sure it's not a dissection. But why does this happen? The machine thinks that this happened. Let's see. I'll put my blue arrow all over it. It thinks that is what happened, but it's wrong. What actually happened is it takes time for the echoes, for the reverberation echoes to bounce back and forth like that. And remember, our ultrasound machines are range finding machines. Range, downrange, distance, depth. These are range finding machines, and they use precise microsecond timing to determine where every echo came from. We've messed up the timing, and therefore we've created, the machine thinks that there has to be a line of echoes inside of the carotid. Notice, by the way, I forgot to mention this just a couple minutes ago, but I got it now, and that's fine. Notice, by the way, that the distance between there and there is the same as there and there. If we see, well, the next line, if there was another line, well, we might not see it because it might be just happen to land on the other wall, just the way I've drawn this. But if it was really strong, super strong, perhaps we would find another, another line down here. Each time this happens, of course, it's weaker because the sound, I mean, there's only a small percentage of sound doing this in the first place, and attenuation and all that, so it's going to be bouncing back and forth and getting weaker and weaker. But in order to see this line, basically we have, this would be the third, this would be the third reverberation echo. The sound would have to go, let's see, back and forth. 1, 2, 3, 4. 1, 2. I guess 3 times. Yeah, 3 times 1 for each echo. All right. So there has to be a reverberation. The echoes has to be bouncing back and forth 3 times in order to get a third line on the screen. And that does happen sometimes if it's a very strong echoes. And by the way, I've drawn fascia and carotid wall because they both are very good at reflecting sound. And if you hit them just right, they really reflect sound. So that in a nutshell is our reverberation artifact. We do see it all the time. It's virtually never helpful. By the way, some of these artifacts are never helpful. Some of them are sometimes, and others are like, wow, if it wasn't for that artifact, I wouldn't have seen what was going on at all. And that definitely happens, especially like with finding tiny little stones. Okay, give myself a lot of room. So that's reverberation. We could demonstrate that again. Oh, did I have? Oh, no. Okay. Okay. Now, there are other kinds of reverberation that are not called reverberation. And that's comet tail or ring down. These are the same thing, but happening between structures that are far closer together. I learned, Melissa learned, I'm not sure about Nana, that there's a difference between comet tail and ring down. In fact, I'll start with ring down. No, I'm sorry. I'll start with comet tail, but I'm gonna. Now I'll go ahead and use this. Yay. You know, just give that a little funnier structure. Okay, I did. Oh, that was going to be an air bubble. Now it's a funny structure that is more or less a crystal. Now, a lot of times in comet tails, we see these in the wall of the gallbladder. It specifies a very specific disease state, not bad disease, but still a disease state. And this is a very specific type of reverberation artifact. The sound, and I don't know if anyone's 100% sure of exactly how this is working, whether it's basically in the case of the gallbladder, it is a tiny little crystal of the cholesterol crystal, to be specific, and whether or not it's just vibrating or whether or not sound is bouncing back and forth. Either way, what you get is a reverb artifact. Reverb. And you have to imagine this is echogenic reverb artifact, not the color of my pen, but so comet tails in my book, not according to this book, Edelman. In my book, a comet tail is a reverb artifact, but it's short and it has kind of an upside down triangle shape to it. But it is reverberation. The sound is bouncing back and forth, or the whole crystal is vibrating. In either case, echoes are continually coming back from the same place, but since these echoes are microseconds, gosh, I mean, these reverb artifacts are so close together that they're not even a microsecond apart as far as their echoes go. And so it's just like echo, 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 echo. Ring down, same thing, except now this time I am going to use I'm going to use an air bubble for ring down. It doesn't have to be an air bubble. It could be a number of different things. Once again, whether this is caused by sound literally bouncing back and forth inside the bubble, or whether the bubble is simply vibrating, kind of like with harmonics, right? Doesn't matter. It's basically a form of reverberation. And so what we end up seeing is these reverberation lines, and by the way, they're very close. They're so close together that what you end out seeing is just a echogenic streak of, like a streak of light down the screen. And in the case of a true ring down artifact, it can go all the way to the end of the screen. And then, in other words, it's, you know, on the comet tail, I drew 4 arrows, let's say 20 echoes came from that same spot. On this one, it's just an infinite number of echoes essentially are coming from that spot. It doesn't stop ringing, therefore you don't stop getting echoes. All the echoes originate from here. They don't originate down here. This is the artifact. In other words, does not exist or fake. All of those ring downs are fake information. They're on the screen. We see them. We're seeing them all, but they're just not really there. It's all, once again, the time error, really. Okay. Comet tail and ring down. Like I said, the book says comet tail and ring down are the same exact thing. I disagree, but that's okay. The shadow knows. Whoops. Now shadows are often, and by the way, these are helpful. I should tell you what's helpful and what's not. These are both helpful. This comet tail, if I find that coming out of the wall of the gallbladder, I know the patient has a condition called adenomyomatosis. It's just crystals of cholesterol stuck in the gallbladder wall. So that really helps me. This helps me identify when I see something like an air bubble where it shouldn't be. If I see a ring down artifact, I just remembered, yes, I forgot I had another picture here for ring down. Hypodermic needle or a foreign body, or just, you know, any kind of metal or anything that would ring, we see coming off. So and oftentimes we help guide needles into tumors or cysts or whatever, maybe a blood vessel. And if we have our transducer, by the way, the transducer should be as parallel as possible with the needle, because when that happens, you get a nice and then let's do a different color to show that this is whoops. Bouncing back and forth, back and forth. Oh, I'm sorry. That's not the one I wanted to make. That can happen. That would just be regular reverberation, but I'm talking about ring down. Ooh, let's see, how close can I get to the needle? I don't know that I'm going to be able to do this, but let's just do it over here where I have the most room. Sound comes in, goes back up, down, up, down. Some of it's released. Boy, I should have drawn this with that in mind. Let's do this. Let me just draw this really quick. I'm just going to do. There's my hypodermic needle. My initial sound beam coming in. Each time this happens, some echoes are leaked back. But each time I draw an arrow in, we basically have a time error. And so what we'll end out over here with is seeing a little bit weaker, and eventually goes away. So reverberation, this image right here with the needle is a little bit, gosh, do they have that example? I don't think they do. It's kind of halfway between reverberation artifact and ring down. It could be ring down because it can go throughout the entire picture. It's reverberation because it's not quite as, you could, basically, if you could see individual lines, here, this is actually a good point. If you could see individual lines, it's more likely reverberation. However, if the lines are just so close together that you cannot see individual lines, then we're really talking more about ring down. But it's the same phenomenon. Okay, now I'm done with ring down. Let's go to shadowing. A couple pictures for shadowing. Now, shadows are also very useful. They can be caused a number of different ways, but for the most part, it's an unusual amount of attenuation. Remember, the machine assumes it has a built-in TGC curve. If you're doing an abdomen, there's a built-in TGC curve. You can mess with the TGCs to your liking, but there's something built in with that. In fact, let's do this. Let's just make my numbers really easy. Let's say I'm just going to put a little hash mark here. We lose every one of these hash marks. We use, this is going to be decibels, 1, 2, 3. And we can call it -1, but it's attenuation, so you should know that it's. Normally, we would expect a constant attenuation through the tissue. Every hash mark, 5, 6, 7, 8, 9, and 10. So by the time we get down to here, the machine assumes 10 decibels of attenuation. And so it listens harder and harder, right? That's what our gain does. That's what our TGC does, actually, our time gain compensation. Every centimeter, every microsecond that goes by, the machine listens a little bit harder. It gains the signal a little bit more in order to create a smooth picture for us. But if we go, whoops, that could have stayed. If we go through a material in the body that has higher attenuation than expected, you could go 1, 2, 3, 4, 6, 10, and then 11, 12, 13, 14. So we jumped up, our attenuation increased. Machine doesn't know, it doesn't know what happened. It doesn't, machine's not saying, oh, there's something there that increased attenuation. Let's alter our TGC curve. Well, okay, actually really advanced machines can alter the TGC curve because it sees that, but the shadow is a useful thing, so we don't necessarily want that to happen. So what happens here is, well, let's see, I need a material. We need some kind of background tissue. This is just regular tissue, a little speckle pattern in it. Should have drawn this first. Okay. The machine doesn't understand what happened. And so all it knows is that down here, it has 11 decibels of attenuation and then 12 decibels of attenuation. That's more than expected. Let's just ignore this. Okay. So this robbed strength. So there's really a lack. So a shadow is a lack of echo information. And of course, our numbers, it really depends on our shadows. So we have shadows that are lightly shadowed and we still see objects inside of the shadow. So that would be a lack of information, a deficit of information, or lack, or how about this? Deficit. Yeah. A deficit of echo information would be a light shadow. A total lack of information would be a very dark shadow. And in a dark shadow, you cannot get anything out of it, because basically in a very dark shadow, whatever this structure is up here took all the energy of the beam away. Okay. And this could be, by the way, one of the things, and one of the major things we look for in breast cancer. For some reason, breast cancer tends to shadow. So you'll see something that looks like a tumor and there's a dark shadow underneath it. It's a bad sign. And the opposite is also true. If it doesn't shadow at all, that's a good sign. Okay. I wanted to make air bubbles, and I call them Dr. Jekyll, Mr. Hyde, because here, I'm going to draw a single circle over here. Dr. Jekyll, Mr. Hyde. An air bubble can create a ring down. That's an echogenic ring down, not hypoechoic. It's hard to do. It can create a ring down. But a lot of air, like in your intestines, which by the way, we don't see intestines or behind intestines very well because of the air in them. We don't see the lungs well. We don't see the lungs at all unless there's something wrong. That's because the air itself absorbs sound. It also reflects. So as sound comes down, a lot of it reflects back, close to 100%. Let's say 95% reflection. Well, if you have 95% reflection and an air boundary, you basically have nothing left. Because also, when you think about it, and the echoes are coming back from whatever is behind the air, they too are going to reflect back. So those echoes, even if the echoes are created, now they have to go through that air barrier as well. So air creates shadowing as well, although it's a messy shadow. It has a certain characteristics that we call dirty shadow. And that is from almost always, I think always, air. So we get dirty shadowing in the intestines for the most part. And I've got to say, air in the lungs, not so much of a dirty shadow, more of a, well, it's a little dark. I would say a little more dark. I think that, by the way, the reason why we have dirty shadowing is rather than a tumor, which is simply absorbing and pretty much absorbing in the form of heat the majority of the ultrasound beam. It's just stealing the power away. Air, when it does shadow and doesn't create a ring down artifact, when it shadows, it's not so much from absorption, it's more reflection. And there's surface reflection, but think about all these different bubbles, all the different surfaces, all the interfaces. Those echoes are just bouncing around all over the place. It's wasting energy. You're not getting any information from inside of the shadow area. But there's just a mess of echoes going back to the transducer, which creates the dirty shadow appearance. We'll see what that looks like. Actually, do we have? No, I don't have a picture available for you right now, but I can get that. Let's see, I think I had one more shadow. Oh, yeah. And just another picture, not another concept, so that's good. I have here a gallbladder with a gallstone. And one way we know that it's a gallstone and not simply just echogenic bile, which that happens too, like little balls of bile, which, by the way, probably will turn into stones. We had pregnant patients. Pregnancy changes your physiology and you're more likely to create gallstones. And I had a student in my first class here in El Paso. She was pregnant. She had biliary sludge balls, they're called. And they were somewhat echogenic, but they were not stones. They did not shadow. If it doesn't shadow, it's not a stone. Later in her pregnancy, by the end of that semester, or the end of probably the next semester, they were full-on stones and they shadowed. So shadowing here, we should be able to use this. There a shadow B caused from that stone. Now we know it's a stone and not something else. Oh, by the way, that's actually, for the fun of it, here's my adenomyosis, these little guys here. That's what I call comet tails. This is something called, well, for now, we'll just call it cholesterol crystals and comet tail. Oh, why not? This is actually a good opportunity. Sometimes we get air in the gallbladder. And depending if it's a lot of air all bubbles along, we'll have dirty shadowing. If it's a single bubble of air, I guess I can kind of imagine why this would happen, but sometimes a single bubble does the opposite of dirty shadowing and creates a ring down artifact. Okay, so hopefully that makes sense. Shadows are a lack of information. It could be a deficit of information, just less information, or it could be total lack of information. A total lack of information creates an anechoic region, completely black region. A deficit of information just makes it darker, but not, still some useful information, still some echoes coming back, but they're all darker due to the weakened ultrasound beam. (10:54), we're doing well. Just two more little subjects here. The thing about this one, though, I don't know that I like the fact that they introduced edge shadow before talking about refraction. We at least know refraction occurs when the impedance, when the speed of sound, see, I got my refraction and reflection confused there. When the speed of sound changes, the beam changes direction. If it's hitting at if it's hitting the surface at anything other than a 90-degree angle. So speed of sound changes. Let me see, I'm gonna need a little help here. Let me draw it from this side. Still on eraser. Okay. So the two lines together represent the beam. The beam has a lateral width, a lateral thickness to it. It's not infinitely thin. So when that beam hits a curved surface, and there is even the slightest change in speed, something weird could happen. Let's see. I didn't draw this perfectly well. let's just take it as the speed of sound changes as it goes through this object, whatever this object is. It's any round structure can do this, a cystic structure, a solid structure. And it is refracted, but only part of the beam is refracted. The part that actually hits it, the other part of the beam is not refracted. So what that creates, remember, beam strength is directly related to echo strength. Beam intensity, which is strength per square centimeter, square millimeter. So it's strength over area, power over area really, but is dependent on the beam diameter. The more narrow that beam, like at the focus, the stronger the intensity. Overall power is the same, but the intensity goes up. If you spread the beam out, this is a spread out beam due to refraction, not because of normal beam spreading. This is due to the refraction. This has a decreased intensity and therefore decreased echo strength. So this creates a special form of shadowing that's not really related to the attenuation of regular shadowing. Regular shadowing is more attenuation than expected. The beam is, the resulting beam beyond the attenuator is weak, and you either get little or no information. This has nothing to do with attenuation. It has everything to do with decreased intensity of the beam. And so our echoes are going to be weaker than expected. Since they're weaker than expected, as in what the time gain compensation expected of it, therefore the machine says, oh, these objects, whatever objects are in this shadow here, these objects must be weaker reflecting than the objects outside, like over here. The machine can't know what happened, and therefore echo strength is weakened. Hypoechoic pixels on our screen, shadow. Stop me if any of these are not making sense. This, we'll only do one last one. 11 o'clock. Yeah, this is good. It's Friday, and it's been a hard week being a duck mom. Okay. Oh, well, we need the title to this one. Enhancement. Dun, dun, dun. Enhancements. So I gave myself a lot of. Once again, let me draw a line. And put a bunch of. So I'm drawing the same line that I did for shadowing. And I'm going to do kind of the same thing here. So let's just keep it, once again, we'll keep it easy. Decibels, they expect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. They expect 12 decibels at this depth. They expect 9. They expect 6 here. Now we have an object in here that's messing with expectations. So this means that the tissue here, 1 decibel of energy loss, of beam loss, attenuation. And I'll go ahead and give it the 2 decibel, even though I have a little bit. 2 decibels here. And then guess what? From, well, didn't do that perfectly well, but I think you get the idea. There is a 0, or darn near close to it, 0 decibel loss there. So we're expecting, let's see, 3, 4, let's just say 3, 4, 5. We were expecting all those decibels to be lost, and then they weren't lost though. So what happens to our, we have the opposite of shadowing. 1, 2, I'm not going to write anything, but I'm going to start down here. 3, 4, 5, 6, 7, 8, 9, 10. Should have been, this was 12, now it's 10. 6 was here, now it's 4. Now 6 is down here now. So what that means is the machine is going to have to say, oh, well, I've only had 4 decibels of attenuation here. I expected more. That must mean that whatever's back here is bright. Let's see if this works. Yeah, that works. This is supposed to represent higher echoes. Machine doesn't understand what happened. It thinks that everything behind this cyst, and that's a cyst, by the way, most likely. Sometimes solid tumors can create a enhancement. In fact, once again, if we go back to the breast, if a solid tumor creates just a tiny bit of enhancement, it's slam dunk, not cancer. But usually it's a cyst. Certainly, if it's obvious, then it has to be a cyst. If it's very subtle, then it might not be. But if it's obvious, it's a cyst. The machine can't understand what happened. It can't understand. It doesn't know that for a couple of, I don't know, centimeters, let's say a couple of centimeters or a centimeter and a half, whatever, that the beam didn't attenuate at all. Then it gets down into tissue again, and that tissue is producing echoes, but it's producing stronger echoes because there was no attenuation in the cyst. The beam maintained its strength through the cyst. And so when it hit the tissues behind it, all of that tissue, which should look the same as the rest of the tissue, but it's brighter, stronger beam. By the way, there's also another phenomenon. A cyst, and this is just a good time to, and I'm done after this, unless you guys have questions, of course. A simple cyst is, it's important to, in ultrasound, it's very important for us to tell the doctor whether or not we think a cyst is simple or complex. Simple cysts are round. They have thin walls. They have posterior enhancement, and it's enhancement or posterior enhancement, same thing. One of the things about posterior enhancement that people forget is that the posterior wall is particularly bright. And that makes sense. That's when this unattenuated beam first hits something that's creating an echo. It's super bright. So posterior wall of the cyst is bright. That's an indication that's a simple cyst. The reason why we have to tell you that, or to tell the doctors this, is that there are cysts that are not simple, and those are more likely to be cancerous cysts. Some cancers are cystic rather than solid. And some things that we think are cysts are actually very, very dark, solid tumors, in which case they probably don't enhance. In fact, they would probably shadow. So all these little hints, this artifacts, sometimes they're just a pain in the butt. Other times, and this is a great example, it tells us so much information about what we're truly looking at, because a cyst isn't always a cyst. A stone isn't always a stone. Our first impressions, oh, I'll tell you one story, then I'll truly be done. I had a patient come in and tell me that she had stones. I said, oh, okay. Gallstones. So I do the exam, and then sure enough, I see bright, echogenic, round structures, moving structures. Actually rolled up on her side, and the structures actually moved along to the dependent area. They went downhill. And I'm like, yeah, you got stones. And I kept on going on. And I don't know if it's 100% because she put that in my mind that she had stones, or if I truly just simply missed it. Her stones, and they were good size stones. Her stones didn't shadow. What I was actually looking at were very echogenic, very bright sludge balls. And the radiologist, who was he was a jerk. He was not a nice guy. Called me up and kind of bitched me out. Actually, didn't even bother bitch me out. He just asked me, "Do you see shadows on this picture?" And I just went, "Oh." I said, "No, doctor, I don't." Mm-hmm. Click. I didn't last much longer after that, but he was universally hated. It wasn't just me. But yeah, so that was a clue, a major clue on a large. I mean, these weren't small objects; these were big, so-called stones. It was a major clue that I missed, and the doctor called me out on it, rightfully so, but he did it like a jerk. And shadowing enhancement, and we'll talk about the other stuff at another time. Too much attenuation, shadows attenuation. Result of too much attenuation, which is the true anatomy structure, reverberation. Yeah, okay, we're cool. We're cool. You guys, any questions today?